Now, neural networks have been around for a long time. And in fact, I mean, when you really go back and look at the history of it, it's 60, 70 years, probably in the 1950s. They first started having ideas. And the idea started with a fairly flimsy, but kind of reasonable biological analogy, which was think about how our brains work. How are our brains capable of doing complex processing when the basic topology of our brain are these tiny, 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 microscopically small neurons that have these synapses or connections between them. And I forget the exact number, but the rough scale is there are hundreds of billions of neurons in our brain, with, I think it's even trillions of connections, of synapses that connect all these different neurons. Each neuron is almost like a nerve impulse. Basically, some things come into it. If the things that are coming into it trigger that neuron based on its parameters or its weights, it fires off a signal and it passes the signal down the line. And then that goes to the next neuron, the same thing. It has some parameters. If the right signals come in and it trips that parameter, it fires and it passes it on down the line. And in this infinitely complex network inside our brains. And so in the 1950s and 1960s, they said, hey, if that's how the brain does it, why can't we create, in effect, a math function that would run on a computer that would, in effect, have these neurons, these very simple little units. We would string them all together, and this would be a way that we could simulate intelligence. So neural networks started in the 50s, in the 60s, continued into the 70s and 80s. It went through various waves of excitement about this as a technology. There were a lot of practical challenges. They were still pretty small. Computing power had not caught up. Availability of data was still at a very small scale. And so back in the 80s, there was really this rivalry between neural network approaches that were centered around machine learning. You feed in data, this black box model kind of learns from that, and that's how you simulate intelligence. Versus in the 80s, I mean, probably most of us in this call would at least vaguely remember these expert systems. And the expert systems was sort of the opposing school of thought, which was, why don't you do what computers actually do great, which is build top-down rules and concepts, build in logic around reasoning, build in some probability weighting of, in this case, if it's a little more of this, then do that, and then build it in very specific domains. And expert systems in the 80s probably were actually winning against these more machine learning based approaches. In the 80s and 90s, there was some continued evolution of figuring out ways to train neural networks more effectively, how you could build a feedback loop. And there were at least three kind of godfathers of machine learning who kept this going, who you'll actually see in the news now quite a bit. One of them leads Facebook. The other is this guy, Jeffrey Hinton. And the other guy is, I think actually, Jeff, he's in Toronto. They are often cited as like the godfathers of all this stuff because they were keeping neural networks alive and doing all the research around it in the 80s, 90s, and into the 2000s when everybody was basically just kind of ignoring it. They were ignoring it because it wasn't really yielding the benefits that everybody thought. And back probably in the 2000s, this little picture on the left is kind of like what a neural network was. You would build up flat, dense, fully connected layers of a neural network. A good example of this was the post office had a project where they wanted to be able to automatically scan handwritten zip codes in the late 90s. And the guy who now runs Facebook's lab, AI lab, actually developed a solution for the post office to read handwritten digits so that they could automate basically the routing of packages. Some optical scanning, figure out where it is, and then route it appropriately. So handwriting recognition of numbers A very, very famous data set got published called MNIST. It's a data set of 50,000 little 784-bit, 28 by 28-bit handwritten numbers with a full set of labels. Again, probably until, I don't know, 2012, 2014, that would have been considered state of the art. And those are the kinds of examples that people would be taught was how can you read handwritten digits using a very simple neural network architecture like this on the left. Starting in around 2011, 2012, obviously IBM with Watson, Google started picking this up, looking at like recommendation systems and how it could enhance their search. Computing power was a lot more than it was. And at that time, they started to really look at how do we start to think about more layers in the model. So even when I first started to do this 10 years ago, you would talk about like a 5-layer model or a 7-layer model with these rows of neurons. And then what really started to take off in the 2010s were convolutional neural networks, which basically were just a slightly different way of organizing the neurons. So it basically organized them in a way that actually proved to be much more effective at learning things like images. So convolutional neural networks really took off. That was considered the state of the art. Machine vision really was centered around CNNs. And again, that's what people probably would have said, even as recently as 6 or 7 years ago, was state-of-the-art stuff, was machine vision with convolutional neural networks. Recurrent neural networks and a whole flavor around them were actually what people were using for language processing. And it was not too good. Very hard to train, very unstable, yielded very inconsistent results. In 2018, 2019, the transformer revolution started. And it's really as simple as organizing the neurons differently. It started with a paper from Google Research. This picture on the left, whether it has a lot of meaning or not, it is a very famous, iconic picture. It is actually a picture taken from that Google Research paper, Attention is All You Need. And basically, the net of it, like stripping away all the kind of fancy stuff, is they came up with a different way of organizing the neurons, all the little parameters, all these little math functions, into something that they called a transformer, using what they called an attention mechanism. And they wrote a paper on it. It's a relatively common sense, intuitive paper. But the net of it is they created a new component to create layers of these components in a neural network. And the net effect of it is it worked better. A lot of the kind of the top researchers are always proposing like different little modifications in the architecture. Well, what if we try this and what if we try that? Sometimes it works, sometimes it doesn't. And in fact, it's very hard at an abstract level to know whether one architecture or another is going to turn out to be better. In fact, some of the truly like leading lights, in AI will publish something, the future is this, the future is this. And then people try it and it just doesn't work that well because there's no way a priori, like to just say, oh, this is the perfect way to organize all of these little tiny mathematical functions to best encapsulate a piece of knowledge that input translates to output the most effectively. There were several innovations that they brought, most of which turned out to work pretty effectively. So they did some things with the inputs. You can see they kind of encoded the inputs in some different ways. You can see they call it a multi-head attention. So in this little orange box, that blows up into a whole series of multiple little models inside of it, just math functions. They aggregate all of those. You see with that add and normalize. They pass that into what they call feed forward, just a flat layer, right? And then that feeds into another layer of it, which continues that cycle. The other thing that was really powerful about this architecture is it could be stacked, it could scale, and it was shown to be pretty stable with training. So model sizes exploded. I don't have the exact number at hand, but for a convolutional neural network, if it had, 100 million parameters, that was really big. And that was, again, 5 or 6 years ago. What started to happen with these transformers, Google rolled out BERT. Right around the same time, OpenAI rolled out a GPT based on this architecture, but configured in slightly different ways. And you can see kind of how they talk about them, like it's 12 layer or 24 layer. I didn't have time to look up the exact number for GPT-3. I think it's like 1,000 layers. Basically, this architecture just repeated over and over and over and over and over again. And again, the weird thing about IP in this space is that all of the researchers publish. So the actual architecture of what the model is, the size, the specs, the configuration, 12 layer, 768, hidden, 12 heads, 110 million parameters. All of that is basically in the public domain. And any of these models, basically, you could create that exact architecture, either taking their pre-trained weights or starting with your own in probably less than 100 lines of code. In some cases, it's as little as a few lines of code. Anybody in the world can create this type of model that will be exactly what Google or OpenAI or Microsoft are using. And in fact, what you've seen is as these models have taken off, you'll find all sorts of open source initiatives where people basically take these models, they train them in some way, they host them, because it's actually that easy to do. The recipe, so to speak, is all out in the public domain. In this case, you can see these are actual models on Hugging Face, and you can literally, with 2 lines of code, just download it. You can see they range from 110 million parameters to 340 million parameters. These are the types of models that would be considered small models today, but they're kind of the size of model that are still relatively easy to handle and execute at kind of a desktop kind of level. When you start getting to models that are in the billion parameter kind of area, those are a little clunky on the desktop. And then once you get to models that are like 5 billion to 10 billion to 20 billion parameters, really clunky and really hard to deal with, really, really slow. The models typically take like 5 to 10 times RAM of the number of parameters. Each parameter is, a 4 byte, float. There's some other overhead associated with it. So you can kind of say, I don't know, half a gig of memory. You can be playing with these. But as you start looking at, say, a 20 billion parameter model, it really kind of hurts your head when you're like, wow, you need probably 50 to 100 gigs of RAM to really be able to play with a model like that. But all of these, if you look at Hugging Face, research papers, you look at OpenAI, they'll usually talk about their models in this way. And they're all stacked up basically the way that simple function is. Function after function after function, all concatenated together with all these different parameters and all these different layers. Now, having said that, a model is just a math function, it's also equally important to realize they don't do much. A model is a math function. It takes an input, it gives an output. That's literally all it does. It basically plays 2 games, and that's it. Okay? And I'll say it again for emphasis. Like, there's no other thing like the model can go off and do. There's basically 2 things you can do with a model. The first is you can run an inference. I would encourage everyone to embrace the word inference. It sounds like a really fancy techie word, but it is used commonly, and it is just to describe the very simple thing of you call the function. You use the model. You pass an input into the model gives you an output. That's an inference, one time. Now, sometimes you'll do a batch inference. And a batch inference is something like you might do for an embedding. where maybe you actually want to pass 1,000 inputs into the model. And most of these models are actually fairly parallelized. So they could accept 1,000 inputs and then give you 1,000 outputs at the same time. But it's the same thing. Input, model runs its math function on it, gives you an output. Nothing is learned in this process. And I think it's really important also to understand that models are not real time. They're not online. They aren't taking stuff in, like learning from it and adapting and adjusting. They're not doing any of that. Like, it's notable, right? And it's been so much in the news. Models like OpenAI's, they'll say it cuts off at, November 2021. Well, think about it. Like, they have raised, $1 billion. They have the best researchers in the world. Why did they cut off, 15 months ago, 18 months ago? It's because it's hard to train these things. It takes a long, long time. So OpenAI, until, I don't know, last month, was actually taking, anytime people would provide an input, they would have an output, they would save it. And they would save it and archive it and put it, somewhere on the side, because in future rounds of training the model, they would use that as input. But the model itself, that ChatGPT model, it's not learning anything. It's not getting smarter. It's not reasoning differently. It's taking in an input and it's giving an output. Now, I'm going to explain a little bit how like a ChatGPT works. But one of the things that they do is they sample from the model. And this is kind of intuitive when you think about it. It's not as if the model just gives an output, the answer is 7. What the model actually gives is it might give over a range of outcomes what amounts to a probability distribution of each of those outcomes. So it might be 98% 7, 2% 6. And so the output of the model can then be interpreted. And it could be interpreted as, well, the answer is 7, because the signal for 7 is 98. The signal for 6 is 2, and the signal for everything else is 0. So you interpret the output as 7. But you could also interpret the output as this probability distribution, where you'd say, you know what? About 1 time out of 50, the output should be 6, because that's what the probability distribution actually is. So if you turn the temperature of OpenAI down to 0, you would actually get, definitively, for every input, you'd get exactly the same output every single time. The reason they turn up the temperature is they're sampling from that probability distribution. It makes it more fun. So what that sampling would do is, yeah, like, if it's 98%, you should probably take that most of the time. But sometimes, just for fun, take the one that was the 0.02. And then sometimes, let's say, and I'll pick sort of an example, like, if it says the president and it has Obama, 48%, it has Trump, 42%, and it has Jimmy Carter, 10%, you might say, well, sample from that. Don't always give me the answer Obama, because that's kind of boring. So sample from that distribution and give me other names. And then once you get other names, the next word gets sampled again. And so it can lead to very different outcomes. But at its core, what's in the model, nothing is changing. It's not doing anything different. The input is coming in and it's giving the exact same output every single time. Okay. Now, the bottom part, training. This is, everybody gets, I think, can get very confused when you start talking about, quote, training a model. Okay. What happens when you train a model is you are trying to adjust the parameters of the model so that the model corresponds with the outputs that you desire given the selected inputs. Now, when you first instantiate a model, just a math function, it doesn't have any pre-learned parameters. It actually typically starts randomized. That's typically how you set it up. You can picture, it's a simple line of code that just says, yeah, give me random for all of those parameters. And so when you start training a model, you're feeding in input in which you have labeled output. And the objective then is through that input and through the labeled output, through the correct answer, is to little by little adjust the parameters of that model so that this black box, this math function, for the inputs that you put in, it gives you the outputs that you expect. Now, a very important kind of subheading to this is there are at least two different ways you could think about training a model. Before 2020, most people started training from scratch. And in training from scratch, you would just create the configuration of your model, your architecture. I've got 5 layers, I've got 7 layers, I've got this. You would initialize the weights in a random way. So so that the initial, you feed an input into your model, it just gives, garbage output. And then you would train it, and you would train it from scratch using your own data and your own samples. Now, what's changed is really over the last probably 3 years, that's a pretty antiquated thing to do. And that was when models were really small, the availability of data was much smaller. But when you start looking at the kinds of models that are being trained, the size of them in terms of their parameters, what they're actually doing, and Hugging Face was one of the first to do it, and it's really awesome that they do it. They publish not just the architecture, like, hey, this is the topology of this model. They actually distribute the pre-trained parameters as well. And it's become a tradition in the research community. Anybody that's publishing a paper on AI, you can't just get away with writing it up. You actually have to provide the code. And it's become a tradition. You actually provide the implementation. So you look up almost any paper, they will have a public GitHub repository where usually you can download all of it, both the architecture of it, but then the actual pre-trained model that out of the box has been trained on whatever objective they've given it. So then the game, beyond the big work of training these sort of foundational models, is fine-tuning. All fine-tuning means is instead of starting from scratch with randomly initialized parameters where your input doesn't know anything about your output, by fine-tuning, you basically start with a base. And a lot of these large language models have been designed so that they have a pretty good understanding of the general working of language. They can give pretty sensible, you pass in an input, it's going to give a pretty sensible output, but it hasn't been optimized for a particular domain or a particular task or a particular industry. And so the whole game is take those models that already have this and then fine-tune it, and fine-tune it by using data that's very specific in the domain that you want to apply it. So how does ChatGPT work? Because I think it's really important to kind of get a big picture view of it. Again, all of us are guilty of this. You think the model is talking to you. The model only knows numbers. You pass numbers in, it passes numbers out. So a very simplified version of this flow. You type into ChatGPT, I wanted to go to the store to buy. Each of those words in that sentence get tokenized, which largely just means it just gets converted to numbers. And there are algorithms, again, all out in the open source, all fairly standard. GPT uses one of the more popular ones, byte pair encoding, that basically breaks down your sentence into tokens, with each word more or less corresponding to a token, but it does sensible things like it breaks up certain syllables and assigns tokens to each syllable in a word just to optimize the representation of the language. It tokenizes it into around 30,000 unique tokens, and then it assigns a number to them. So what actually goes into the model is not, I wanted to go to the store. It doesn't know anything about store. It doesn't know anything about English or words. What's being passed into it is a tensor, basically just an array or a list of just numbers. 2, 9, 12, 36, 12,362, a string of numbers. That gets passed into GPT 3.5, which is just a really big model. It runs through all the layers of that model, and then it has an output. As I was explaining, there's a sampling in these types of models. So they have an algorithm that probably is running in parallel multiple beams. So in effect, they'll run 5, 10, 20, I don't know how many, basically strings of potential candidates of text. They then, out of that sampling, they'll rank or prioritize which of them seems to have the most logic or in various other tests have scored the highest. So this sampling algorithm is basically a post-processing of the output that comes out of the model. And then they have at least one, if not multiple, auxiliary models that then do all the things like content moderation, moderating toxicity. And that's a model that's basically been trained on, hey, does this output look okay or not? If it doesn't look okay, go back through some loop here because we're not going to give toxic output. And then this whole thing has been going on with just strings of numbers. Then finally, it's reverse tokenized. They look up those numbers, convert it back into words, and then you get your answer of, what will you buy at the store? But again, in between, at the core of this model, I just can't emphasize enough, it's just a math function. That's it. Again, it isn't learning, it isn't adapting, it isn't adjusting, it isn't weighing, it isn't doing anything other than you put in an input of numbers, it has all of these fixed parameters. It gets to the output of the math function. It goes through a little bit of this post-processing, then they convert it back into words. That's how most of these models are going to be set up. A core model with some sort of auxiliary processing or models that will do further work on it before the output actually gets passed to a user.